All right. All right, so starting with the guy on the left, again, this is a 6-member ring. It's not a cyclohexane, but I sort of put the oxygen there. Still be able to sort of draw this in this sort of chair conformation. And one of the reasons why I put the oxygen in there, right, was to make sure that this molecule is chiral. To make sure that we're staying honest with our sort of absolute orientation of this. Okay, so if you guys remember, chair conformations, again, it's like anything, sort of drawing molecules in 3 dimensions, can be a bit challenging. The chair conformations are the cyclohexane rings, right, put into an orientation that looks like a relaxing chair. At each carbon around here, there are multiple positions. And what you have, right, is a rotating sequence. Just a quick refresher on chairs. Right, you have this sort of rotating sequence of events where sort of as you go around the molecule, right? You know, you have groups that are kind of in line with the plane, right? These are sort of up and down, so we're down, up, down, up, right? What are those called? Those are called axial, right? And then sort of going around the outside, again, we can't necessarily show the dimensionality pointing towards you guys, but the idea is that all the other groups are sort of, instead of being vertical, these are sort of all mostly in sort of direction towards you guys, and those are equatorial, right? Hopefully you guys remember that from last year, and it will become important when we start talking about stereochemistry of sigmatropic rearrangements, and that is that which position is higher in energy. If there's going to be a group, is it higher energy in the axial position? Is it higher in the equatorial position? In general, if we remember? Hearing axial, right? So it's in the axial position. It's generally the one that's sort of higher in energy. And there's a few ways, if you forget if axial is bad or good, there's a few different ways that you can sort of do this. Right, the one way is to sort of recognize, say, for example, if this is a CH3 group, right, you can sort of recognize that they're coming into closer contact with these protons that you see up here. Whereas if you, say, for example, have a methyl group out at this position, you don't necessarily have that sort of close in proximity. In truth, if you really want to get to the heart of it and see it a little bit better, because I get that sometimes it can be tricky to see it from this standpoint, you can go back even further and start looking at Newman projections, right? And recognize, for example, that what you're really referring to, you know, say, for example, if we're looking down that bond, right? This carbon in the back, right? If we're doing a Newman projection, say, for example, down that carbon-carbon bond, sort of this carbon's the one in the front, this one's the carbon in the back. There's 2 protons, really only 1 carbon, right? And so what you're looking at here in reality is what's the relationship of these groups to that carbon. And what do you notice about the relationship of the equatorial to that carbon? Now, you guys remember Newman projections? Right? Newman projections are those sort of three-dimensional depictions that show this. So based upon E, right, these positions here are sort of the gauche. I forget how to spell it. Gauche. Say again? C-H-E. Gauche. And these are sort of anti, right? So the ones that are in the closest proximity to A are the gauche, and the ones that are basically anti-periplanar to this is the anti. And again, this is what you can sort of look at, for example, if you remember the anti from, say, for example, elimination chemistry, when you sort of go from one stereocenter, when you get a specific alkene stereochemistry based upon that. So what do you think is the relationship, say, for example, between this methyl group and that methyl group? Or that methylene, I should say. Is that gauche or anti? I'm hearing something for gauche? For anti?
Oh, that's yes.
What's that? Oh, you're IT.
Yeah.
I didn't call it ITS.
Who you call?
No,
For your projector.
I don't even have a projector.
Fair enough.
There's a class after me at 10:15 or 10:45, and I think she, or I forget if it's Maggie or so, maybe come back at 10:45 because that's between, that's when they use projectors. All right. So if you're struggling to see it, this is gauche. You got to recognize that the orientation of things, if you've got anti, the only two other options are gauche, right? And so what you should be able to tell is that the equatorial is in fact anti to that. Can you guys see that? That this methylene, that this methyl group is anti to that methylene, and that should be a little bit easier to see. So you should recognize that based upon this carbon, right, this and the equatorial position, if you drew the Newman projection, right, that would be in between the two protons. It's going to be the lowest energy, which means by virtue of the fact that there's only one potential group that can be in the anti-orientation, then this axial group is in fact gauche, which means that it's got that steric interaction there. Okay, so this is just a quick refresher on chair conformations. A reminder that and again, a reminder of these concepts of anti being higher energy, equatorial not being better. So that's going to be important. What's also going to be important is drawing chair conformations. Like anything, this is, again, where your artistic ability or lack thereof can benefit you or hurt you, right? Because if you can draw things and they look good and you can sort of see from the drawings, it's going to be important. If your drawings look like, you know, scratch, right, it's going to be perhaps difficult to see things. And so one trick, if you struggle to draw chair conformations, is to realize that, I don't have my multicolored chalk here, let's see if I can sort of see what fiber is. Well, I'll try my best to sort of get you guys to see this. But in general, when you sort of have a chair conformation, what you recognize is, that's not very good. Is that when you draw these chairs, that chair, again, we just talked about the anti-relationships between everything. In fact, this is really a series of tetrahedral carbons where, you know, you sort of have a lot of anti and gauche interactions around one another. So you recognize that everybody can sort of very readily see that those lines are in fact parallel to one another. A good chair conformation, these two lines are also going to be parallel to one another, okay? And then meanwhile, these lines are going to be parallel to one another. And so within that chair conformation, there's going to be really three sets of parallel lines if it's drawn well, okay? Now, obviously the equatorial, right, all become completely 180 degrees, right, from these groups here, or I should say 90 degrees, so 190 degrees, sorry, from these groups here, right? So each of them are in the plane of the board, and usually people are pretty good at being able to draw those groups. You just go up or down, and again, they should be 90 degrees from the sort of lines that you show here. The challenge can often be, and then again, you have this sort of lines here that are equatorial, that are going to be in fact parallel to these, where students can often struggle to draw, and what can often be challenging to students is these sort of equatorial ones that are closer to you or closer, or they're further away from you. And so what you can sort of recognize is that this bond there is in fact parallel to this one here. This bond here should in fact be parallel to that one there. This bond there should be parallel to that. Vice versa, and then likewise this should be parallel to that. The nature of this is that this bond here, the one that I've shown here, I've done it parallel to there, but really what this is this is reflective of the fact that this carbon, whatever, methyl bond, so I guess I have it drawn here, is in fact anti to this bond there. This bond here is anti to that bond there. And so when you think about it in terms of anti and gaussian, specifically the anti, recognizing that each group has some other group that is anti to it, you should be able to get there. So again, this is just a trick. Not a trick, I don't want to call it a trick, it's just a way to think about how these should be drawn. All right, with all that, now the question becomes, how do we draw this when we have a molecule? How do we draw this in the appropriate chair conformation? And one of the things that we can often do, at least what I generally like to do, is start just by drawing a chair conformation. Doesn't matter what you draw, because we haven't given any information to it quite yet. That's not the best chair, based upon what I just said, because that's not quite parallel there, but it's maybe a little bit better, just like that. And somewhere on this molecule, we have to put something. We have to start by putting something somewhere and sort of basing ourselves. And just based upon the proximity of anything, I would probably just start with that oxygen, just to sort of, and then build from there. And I'm going to stick that oxygen right at this carbon here, okay? And what I'm going to choose to do is if I start from that oxygen, I'm going to just number these for my own sake. 1, 2, 3, 4, 5. And what I'm not going to do is I'm not going to make the confusion right now that I'm going to put a group at 1 and I suddenly want to put it at the lowest energy conformation. It may be the case that that methyl group is in the lowest energy conformation, which would be what? What's the lower energy? Equatorial. So it might be the case that that methyl group is equatorial, but I'm not going to make that assumption. I'm going to ask the question, based upon how I have this molecule drawn, I'm flipping that molecule that way. Is the methyl group at 1 going up, or is it going down? So if I take this group, and I've obviously flipped it this way, where's the methyl group going? It's going up. All right, so at up, is up going to be equatorial or axial? Sometimes it's best to just draw things there so that you can see it, right? So let's draw both of them there. And is the methyl group going to be the one that's equatorial or axial? Equatorial, right? And sometimes it's helpful to draw that proton at those carbons as well. It just helps you base yourself. Now we've got 2 and 3. It's in the same orientation, right? If we draw the groups in there and not assign them, but just put some sticks there that we'll fill in later. Is the methyl group at carbon 3 going up, or is it going down? It's going up. Good. Okay, and so, as it turns out, we got lucky here, and we ended up drawing a molecule in the orientation that was, in fact, the lower energy of the 2 conformations, because both of these are equatorial. But you should be able to, in these cases, draw the reverse chair of it, where you'll see that there'll be axial and so forth. And that becomes, the ability to draw axial and equatorial and converting through them becomes a little bit important to this, but it's going to get a little bit more complicated because when we start talking about these sigmatropic rearrangements that we're about to get into, the difference between, say, a 6-membered ring and just 6 carbons that we're going to get to, there's the ability to potentially break open up or close that, which we don't necessarily have the option of here. Okay, so we'll get back into that in a second. All right, so chairs, we'll start getting the 3-3 symmetropic rearrangements in a second. I did want to get to something here really quickly that I think might help. So again, as you guys recall, I've told you guys what's going to be what you need to be able to do for the quiz next week, right? You've got to be able to tell me Diels-Alder reaction. I'm going to give you the starting materials. I'll give you an alkene and a diene. I'm going to ask you what the product is, and you've got to tell me what the product is. Hopefully you draw a Diels-Alder product. That will be the first part of it. And then you'll have to draw me the correct regioisomer. And then you'll have to draw me the correct stereochemistry. Maybe we'll break it up in terms of which components of those are correct. Right? And I think, or I hope, that the order of difficulty sort of raises. At least drawing the correct bond connections is kind of the first step. Hopefully that'll be easy. Then when you consider the possible regioisomers, that's usually something that students can handle a little bit better. And the challenging part often becomes that last part, the sort of stereochemistry, the absolute necessarily, but the relative stereochemistry that we're getting into. And as we discussed yesterday, when the Diels-Alder takes place, you can get sort of two different approaches. You can get more than two different approaches, but two that are related to the diastereoselectivity of these. And those are endo and exo. Sorry, exo and, did I say exo twice? Endo and exo. And when we're saying endo and exo, what we're referring to is, in essence, the positioning. Every Diels-Alder, right, is going to be starting with a diene and an alkene. But in general, what we have, right, is we'll have groups. Say a group. And the endo or exo is reflective of whether when it approaches, that group is going away from the diene or it's going towards the diene. In other words, as that bond is forming, is that group, say for example, overlapping with the back side of this, or is it going away from it? So sometimes the terms exo and endo can be confusing when, say for example, you have a molecule that has two groups that are, say, trans. I often like to just sort of keep, in this case, it a little bit open and say that, oh, it's exo is reflective to this group and endo is reflective to this group, right? So that you guys, the sort of term endo product becomes relevant relative to what specific group you're referring to at that point. But at least on more simple molecules like the one that we've shown here, if I start to bring these a little bit closer to one another, right, these are the bonds that are forming, and so as is drawn here, would that be the exo product or that would be the endo product? Which one? As is drawn? Is the group on the alkene away from the diene or towards the diene? It's away, so then it would be exo. Right? So this would be the one that would go exo. And the one that would be going towards right? That one would ultimately be your what? Endo product, right? So this would be the exo, and this would be endo, this would be endo, and it's the other components, the sort of the substitution on the alkene, in this case, is pointing towards the sort of the back side of that alkene. And as we sort of discussed, and what is discussed in your book, is this idea that sterically, as was brought up last week, somebody was, I think, going to argue that exo would perhaps be the product of the form based upon sterics, which I think would be the intuition, would be assumed that, well, we wouldn't want all the spinach. Sometimes there's groups over here, sometimes there's not, but regardless, you would generally want to put the groups sort of away from where there is stuff, but in fact, the products favor the endo oftentimes, in fact, in very high selectivity, in large part because you have additional p orbitals here, at least this is the thought, that while they're not participating necessarily, that's not where the bonds are forming, you can begin to get pi-pi stacking, which is a phenomenon in chemistry that when you have p orbitals, sometimes they like to stack on top of one another, and that's a favorable interaction. And so you've got a couple p orbitals back here, you got p orbitals there, you got p orbitals there. Those have this what is called sort of pi-pi stacking interaction at the transition state. So this becomes a sort of kinetic product towards the answer. But so that maybe I can explain and that can make sense. The challenge in some of these cases ends up becoming, well, what's the result? What's the stereochemical result? And this is where people, I think, can struggle. And what I would say to start with, and one of the things that we did yesterday that I think kind of helped, is when you start to draw in your protons, and let's just start with the exo for now. Well, we'll just go with the exo, and then you guys can do the endo on your own time. It's just going to be the reverse. Right? When you have these groups, and when you start to realize that ring it is sort of forming, you look at this carbon here, right? I mean, what you're looking at is you're making a bond between ultimately this carbon here, that carbon there, that carbon there, that carbon there, right? So this is ultimately where you're forming the rings. And it's at those carbons where you're going to be going from sp2 with, I guess, alkene stereochemistry, potentially. You're going to be going from these sp2 carbons that are planar to sp3 carbons, which subsequently have some stereochemistry to them. And what you notice, I think what becomes fairly clear here, perhaps, and it's one of the things that sort of discussed yesterday, and maybe this can help you. Ultimately, at the end of the day, you guys, this is something you guys have to sort of work through on your own, and you have to sort of see this on your own and battle with this. But this might be helpful. We were just talking about in the chair conformations, right? How when we draw these structures, we like to have, you know, say for example, groups that are anti to one another, and there's a sort of aspect of parallel nature to the bonds, and so forth that are sort of opposite ends of the spectrum of one another. But really at this carbon, obviously this carbon-carbon is going to be in the ring. What you're really thinking about is the relationship of the two groups here, and what is in essence the two groups here. The one group being the proton, the other group being the methylene. Does everybody see that? Do you want me to say that again? So this carbon, right? This carbon-carbon double bond is what's going to be in the six-membered ring. So that's going to be part of the ring. If we're thinking about the stereochemistry ultimately that's going to form here, where this is going from sp2 to sp3, you really have the two groups. And so it's really those two groups that we're focused on. At this carbon here, this carbon-carbon double bond here is going to become a single bond, but this is also going to be part of the ring. So on this back side of the carbon, it's really these two groups, this proton and this methylene, that sort of ultimately reflect the stereochemistry. Obviously, you're making a bond there. But so in essence, what you're sort of looking for is these two groups and where they end up on the ring in relationship to these two groups. Does that make sense? Okay.
Repeat that.
What you're really looking for is these two groups here in relationship to these two, right? And when you look at that, I mean, what strikes me, and I think I sort of noticed it in office hours with some people yesterday, is do you see any parallel component to any of these? Do you see any of those four groups that we're looking at, or the 2 and 2, do you see any aspect of them that might reflect some anti-relationship? Jessica, you're nodding your head. Maybe it's my mistake?
No, I guess the proton on the top proton bound versus the methylene.
Yeah, absolutely. Pretty damn close, right? Pretty darn close. Pretty darn close, right? That proton and that group there are, one's going that way, the other one's going that way. So because of that, what do you think is going to be the relationship between those two once you form the ring? They're going to be anti to one another. They're going to be on opposite sides of the ring. Does that make sense? Right? This is going in this direction, that's going in that direction. When they form, and when they form that ring, well, the one going in this direction is going to be on one side of the ring. The one that's going in the other direction is going to be on the other side of the ring. Does that make sense? And so when you draw this product, right? As it's sort of coming up, we've got the group coming from the top. So if we're just sort of looking at absolute stereochemistry right now so that we can see that this is happening, when we form that ring, is the methylene going to be going towards us or is it going to be going away from us, the CH2, CH2? It's going to be going away, right? So let's just start ourselves by basing ourselves there, right? So we're going to get, so that's going to be the methylenes inside of here, which means the protons are here. And since those methylines were what Jessica was just focusing on to say that they were anti to, what were these parallel to again? Somebody else? Chaim? They're parallel to this proton. And so if at this carbon, we've got to decide whether we want to put the proton towards you or away from you. If it's anti to that group, do we want to have it going towards you or away from you? It's going to be going towards you, right? Because it's anti to that group. And so again, you guys know how I feel about tricks, and I'm hesitant to call this a trick, because I hate tricks. But what this is all about is having you guys see, ultimately, what's sort of happening here. So I don't want this to be a trick per se, but it's a potential another way that you could look at it that might help you see, ultimately, what the stereochemistry is going to be. And it's sometimes easier to see, and we were discussing yesterday that sometimes when you have the rings, sometimes it's easier to see, but you could do the same thing if there's groups there as well. It's just what is the group that's there? And is that, what's the relationship between this group and that group that's coming over in the other direction? And so this would be the exo product, right? And if we inverted the stereochemistry, that would be the endo product. And so, yeah.
The other way, you have three planar bonds on the typical carbon with the proton.
Where am I looking? Just tell me when to stop.
Oh, keep going, stop. Yeah.
Okay.
So the other way to depict this would just be that as a dash, just making sure that.
Yeah, once I set the carbons coming towards you, you kind of know that the other one's going back, yeah.
Can you draw the stereochemistry?
The stereochemistry for the endo, that's a little too small. We would just invert it. So these would just be going back, and these would be coming towards you.
But the other one would be deeper.
Yeah, I want to get to some of those 3,3 sigmatropic, but what I would certainly recommend you guys all do to confirm that this is making sense to you is I won't go through the other one, but try to do the endo through the same way on your own and make sure that you come up with the correct answer, which should be the opposite. So that's something you guys can do on your own time after class, but you should all be able to do that. And again, this is hopefully a way to look at this selectivity that'll hopefully be helpful for you, okay? All right, now back to chair confirmations. All right, so we discussed, this is, again, as I sort of said in the past, I sort of view the Diels-Alder and 3,3 sigmatropic rearrangements as a really nice medley, if you will, of chemistry that you've learned the last few semesters. And what 3,3 sigmatropic rearrangements are reactions where you have a sort of a six carbon, it doesn't have to be 6 carbons, as we'll see, there can be an oxygen thrown in there as well, but you sort of have a 6 long compound with double bonds on sort of the ends, okay? And what ends up happening in this chemistry is, we sort of refer, there's this sort of magical number of 6 electrons again that we see here that becomes one, you don't want to call it a magic number, but it's sort of one of these. We discussed the importance of 6 electrons for aromaticity. We discussed this idea of 6 electrons in a Diels-Alder cycloaddition. And now here we see this magic number of 6 carbons again for a 3,3 sigmatropic rearrangement. ultimately, as is the case of what I've shown here, we have that product there, which is, in essence, the identical molecule that we just drew, right? Just sort of flipped over. So this is a 3,3 sigmatropic rearrangement that just remakes itself, right? But again, it's the simplest form of it. Why is it called 3,3 sigmatropic? You know, I don't know that it's all that important, but I guess the reason why they will often refer to it as this is if you think about what's sort of happening, you are sort of looking at a system where you have sort of 3,3 groups, one that's sort of, you can imagine, bearing the negative charge, the other group that's bearing the positive charge, and this is ultimately what's forming the ring. So another way you can think about this is, which I don't know is all that helpful, but if we think about maybe just this first arrow, for example, what you're sort of sitting here with is a molecule like this, and then your sort of cationic species here, or I don't know, I'm just sort of getting ahead of myself, getting into areas that perhaps are a little bit too complicated. But this is, I think, one of the reasons why they call it 3,3 sigmatropic. You're sort of breaking a carbon on one side of the 3, and it's sort of ending up on the other side. Is kind of the idea here. So it's 3,3 sigma. You're breaking sigma bonds. So this is sort of why they're called this. So much like Diels-Alder, when you see a diene of this nature, and I say heat it up, there's going to be a series of more and more difficult things where you have to sort of step up your game at each level. And the first is simply knowing that this is a reaction, and hopefully you guys, by virtue of being here and listening to me, could at least draw the product just verbatim of the 3,3 sigmatropic rearrangement. The more challenging one that's going to take a little bit of practice is what we'll get to is the stereochemistry. And so let's just start by asking a fairly simple question, and that is, what is just generally, don't worry about stereochemistry at this point, but what is the product of this 3,3 sigmatropic, absent from stereochemistry? We're not going to worry about stereochemistry here, but I hope that you guys can all look at what I drew on the top, shuffle the arrows around, don't worry about stereochemistry at this point, and just see what the new product is from this 3,3 sigmatropic rearrangement. Okay, so you guys, this should have been fairly easy if you struggled with it. Perhaps something that you may want to do, because sometimes if you did struggle with it, sometimes students struggle when you're considering ring systems. But you can only just number your carbons and ultimately see what's going to form, right? So if we go around this and we go 1, 2, 3, 4, 5, 6, we push our electrons around, right? We're making a double bond between the 2 and the 3. We had a double bond between the 2 and the 1. That is now going to be a single bond. We're making a bond between the 1 and the 6. We had a double bond between the 5 and the 6. Now that's becoming a single bond. And now we're going from a single bond of the 4 and the 5, and that's becoming a double bond. Right? And so that's just 3, 2, 1, 6, 5, 4. And now we have to sort of consider what else is there, and what do we have? We have the 2 methyl groups, right? One of the methyl groups was at carbon 1, so we should still have a methyl group there. And there was still a methyl group at 6, so there's going to be a methyl group there. And so this is the product, absent from any stereochemistry. This would be the product of this sigmatropic rearrangement. Okay? Now, what you notice in this molecule is that the relationship of those 2 methyl groups, there's a couple options, right? Once we start to introduce stereochemistry, right? They could both be, I guess, in this sort of confirmation, I guess you would call them syn, right? Or they would both be going, let's just say they're both dashes or wedges. They're both going the same plane of the board. Or one could be a dash and one could be a wedge, or vice versa. And as it turns out, the nature of sigmatropic rearrangements is such that depending upon the stereochemistry that you have at these alkenes, it will change ultimately what the stereochemistry is here. So on the one hand, you get a conference, or at least a high level of stereoselectivity in this process, and the nature of that stereochemistry can change based upon what the stereochemistry of the alkenes is. Okay, so that's just the sort of the big picture. The challenge now is how do we figure this out? How do we solve this, and how would we go about determining what that would be? Okay. And this is where we're now going to go back to what we were talking about at the beginning. We're going to go back to chair conformations. And what I'd like you all to do, just really quickly, not really quickly, but I'll give you guys a few minutes, because I think it's worth it to have you guys try this, and if you don't get it right, that's fine, at least we'll be active and learning here. Try to draw, this is a 6-member ring as is drawn. It's not a 6-member ring, it's an open 6-member ring, but it is a 6-member ring. What I would like you all to do is spend a minute or so trying to draw that molecule in a way that would be reflective of a chair conformation. Okay, so draw it like a chair conformation. Make it look like a chair. If you have to draw a chair, a full-out chair, and erase one of the bonds, do that as well. If you've got a pencil, I love pencils on exams, right? So you want to draw your chair first, erase one of the bonds, and then start building around it. But why don't you guys go ahead and try that. Try to draw this as a, or at least looking like a chair. Does everybody understand what I'm asking for? I'm not asking you to put it in the highest or lowest energy conformation at this point. I'm simply asking you to try to make it look like a chair. Can you guys see that in the back okay? Oh, you got it? Yeah, Todd. It doesn't. Well, we haven't established the stereochemistry here yet. So we don't know, that could be either or at this point. So we're going to focus on this one first. Ultimately, your ability to draw a pseudo-chair conformation of this, Taj, will help you figure out what the stereochemistry is there. So, yeah.
You want us to draw the transition state of it?
Not yet. Not yet. That's going to be the next step. Got it? Okay, does any brave souls want you, Todd, you want to come over and try it? No, right on the right square. It's actually not bad. I'm glad you did it. So that looks really good, actually. So this was actually a very nice looking chair. There is one problem, so I'm kind of glad that this mistake was made. But besides this one mistake, that's a really good-looking chair. Anybody know what the mistake is that Taj needs to be careful about for next week's? Yeah.
Put them up. Like, you have to actually name it.
No, you don't have to name it. No, it's not that you have to name it.
Is one method going up, one is going down?
Well, here's the dotted line, right? So that would sort of help complete the chair. Is one going up and one going down? I'm not following you.
Can I go over there? Both the method groups are swimming are.
No, so Taj thinks she knows her mistake already.
Is it because some of the lines are like parallel?
No, your chair looks wonderful. Your chair looks wonderful. It's not that. There's something. I'm sort of glad that you made this mistake because I think a lot of people will make this mistake. Saul, what do you think?
You know, both the method groups.
So-
One is going up, one's down.
Well, so there's a concrete answer. So the fact that you're sort of wavering on it, I want the concrete answer. Which
She drew like their cis, but it's supposed to be trans.
yeah. So that's it. Can you say that louder, so everybody?
She drew them cis, but it's supposed to be trans.
Yeah. See, what's the stereochemistry of that alkene? What is that? Yes, that is cis. And that is cis. But they are actually trans. And I think, Taj, I don't want to speak for you, but I think the reason that she did that is this was pointing in this direction over here, and that was pointing in the direction there. And when she drew it, she just wanted them pointing in the same direction and wasn't recognizing the relationship between that. Am I right there? That's probably why you did it, because of what orientation they were here. So you have to pay attention to what the relationship of this methyl group is in relationship to this. As is drawn, this is cis, and this is cis. But in the starting material, they're both trans. So, Taj, do you want to come up here and try and correct it, or does somebody want to try and correct it for her? I'll just do it. So the trans would be there. So I'm just going to put this as, and then here, now let me ask you a question. Of the groups that she has there, right? She could have drawn this a different way. Actually, I don't think she could have. I think that no, she couldn't have. And I'll get back to this in a second. What at those carbons, and again, I get that this is an sp2 carbon, but at least based upon the image that we have here that's sort of reflecting the chair, I think it's worth just sort of noting, are the methyl groups that she has there, are they more like an sort of pseudo, or are they more like an pseudo-axial, or are they pseudo-equatorial? Yeah, they're more equatorial-like, right? She drew them coming down. These are more like axial, and they could be axial, and you'll notice right away that the axial carbons would be the one that would come from the cis double bonds. But the trans ones are the sort of equatorial. And this gets back to what we were saying right at the beginning of class when we were discussing how there's this sort of parallel nature of the sort of equatorial bonds being anti-periplanar in nature to that inside part of the ring. These aren't anti-periplanar per se. Well, they are, right? They're anti. They're trans. They are anti to one another. Okay, so that's the first step of figuring this out. Yeah. Oh, you were just. Oh, okay. So this is the first step, is to be able to draw the molecule. And in this case, there was really only one way that you could draw it. We're not going to be able to draw either of these in the anti-conformation. Sorry, brain fart. Yeah, you're not going to be able to suddenly switch one and draw it in the cis conformation, right? Alkenes are sort of locked into the stereochemistry that they have. So now what we have to do is we have to think about, and somebody brought up the transition state. You don't necessarily need a transition state per se to draw these. This is sort of, I guess, maybe the pre-transition state assembly of this, if you will. But what's going to happen, right, is that we are going to move these electrons around in that fashion. And this is the first challenge, okay? So actually the first challenge is get it into the pseudo-chair conformation. The second challenge is draw a product that results from that without making too many changes. So what I'd like you all to do is just redraw this molecule. Everybody spend a moment. Try to redraw this molecule. Keep it as the pseudo chair. And what should happen, right, is you should get double bonds here, and the nature of these bonds, they will suddenly go from being sp2, right, that one of the bonds form, now they're going to be sp3. Okay, so everybody spend a little bit of time trying to draw the products simply by moving the electrons around and redrawing the molecules. So don't change all that much. You're just going to be changing where the electrons are, right? So all the carbons, everything should basically stay in the same place. You're just sort of moving the electrons. So you're going to be breaking this bond, making that bond, and moving the two alkenes. So everybody spend time doing that. Yeah, so.
Oh no.
Well, let's get, I just want to give everybody a few moments to try and draw this on their own. Okay, how do you guys feel about this? Show of hands, just out of curiosity. Show of hands for people that feel like they were able to draw the new product. That's good. People that don't feel so good, don't be ashamed. It's okay, well, I'll assume that people didn't raise their hands the first time and feel so good. Does anybody, any brave soul want to come up and try this? Sure. What's your name? Sorry. Yeah. Yeah. All right, let's see what Yannick can come up with. Yeah, it's going to be tough to draw because you're right. You may want to start over here because that line gets in the way.
Yeah.
Yep, keep them in exactly the same way. Yep, and then I would put in I always like to put in the protons. I think it's a good idea. I think it's a good habit to get in when you're dealing with structures like this, to show the protons, simply because, it helps you see it, right? So what do you guys think? You guys like that? Yeah.
So the double bond should be six each other. That's what we had.
The double bonds were, wait, hold on. No, wait, what?
Because when we drew it without a chair, they were.
The starting here, let me just the starting what we started with was this.
Yeah, and then when you converted it, it became cis.
No, the double bonds stay. You're not going to change a double bond from cis to trans. Yeah. Now you. But when Taj initially drew it, she made, I think, a common mistake, and that was she was focused more on the directionality of these groups and not necessarily the relationship of those groups to the rest of the molecule. So it's important that you double check yourself to say, all right, that double bond was trans. When I draw in that chair conformation, is it still trans? Because it's common, the mistake that she made, so I was kind of glad that she made that mistake because it is a common one. So you just got to sort of double check yourself and just say, hey, is this, but yeah, so you got to stay that. But then in the product, once you go through, it looks good. Saul, you got your hands up.
So, stereochem is conserved, but
Let-
regio, like, whether it's cis or trans, changes.
Oh, careful. I don't know. Maybe. I don't know. I don't know. I have to see it.
Part of the first part. Is
Yeah, neither. So stereochem. Well, wait. So sorry. One more time.
So in the example we've done, it looks like the stereochem is conserved. They're both still like before.
Oh yeah. yeah. Yes. Yes.
Like,
Yes.
if
Yes.
I'm
Yes.
doing
Yes.
this in a reaction, I want to get stereochemical things where they're both can be equatorial or both axial.
Well, yeah. Yeah. So yes, you're not going to be changing things. Things are going to stay, and this just gets back to you're just moving the electrons around and you're staying put. So later on, we'll get to maybe one where there's possibilities. In which case, and we'll get to one maybe after this, where you may have to look at multiple versions of this, where one could be axial and one could be equatorial, and you have to sort of exactly. Or if there's groups over here that might, you might relay absolute stereochemistry here to over there. So we'll get to some of the more challenging ones. This was just a sort of the basics. But they can all be seen through this. So the important point is, again, first step, show it in the pseudo chair. Make sure that your alkenes and all your stereochemistry is correct. Next step, push the electrons around. Make sure that you draw the molecule just as was done here. So this is beautiful, perfect. Notice that nothing's changed. The protons are pseudo-axial here. The protons remain pseudo-axial there. And maybe this is what you're saying, Saul, is the methyl groups are pseudo-equatorial here. In the product, they remain equatorial. Yes, right. Okay, so that's the first challenge. Now there's a big challenge here. And this is, do we leave the product this way? And if I told you that you could leave the product there this way, it might make it a little bit easier, but I'd like you to usually draw it and then be able to sort of open this up and look at it a little bit more difficult. And so maybe when I ask the question on the quiz next week, maybe there will be credit for having it at this, and then there'll be some points that will then be from getting it to this, to the opened form, right? We want to go back to something that's a little bit more simple, or at least flat, and so I guess the question becomes, I drew it like this before, but I could also ask a question, 1, 2, 3, 4, 5, 6, right, like that. So on either one of those, I'd like you guys to be able to convert what you have shown me here. I'd like you to be able to show this whether you want to have it this way or whether you want to have it this way. So let's spend a moment trying to relay the more three-dimensional chair depiction here into this last one. And so again, when I ask the question, I'll probably break it up into parts because I recognize that this last part can all be a challenge, and each step you guys have to sort of work out together. So let me, I'm going to erase this side here so it gives us some space to play with this.
Should we include stereochem when we're writing it?
Well, RRS?
Well, just like in or out.
Yes, that's what I'm saying. This is the question here, is what's the relationship? Because that was sort of the initial question, right? Are these both coming towards you, or are they both going away from you? Yeah.
Yeah, one's going into
So I have a vote for one going in, one going out, based upon the at least more cyclic version.
when you open up it's
So I don't hear any. Do I hear any? Do I hear any? Anyone against that?
because when you open up it flips over.
Well, so we're not asking when it flips over yet.
Never mind.
Yeah, we're just focused here right now, and then that'll be the next part. So on this, I think it seems like I'm not getting any resistance to this idea that one's coming up and one's going down.
One's drawn like that, but drawn over there.
Yeah. So we'll deal with that separately. We'll deal with that next. So there's
Top right. Top right only looks equatorial, one looks up, one looks down.
right. So on this one right here, again, it's about where we're positioning ourselves. So if we're looking down at this, if we think about this as being 1, 2, 3, I forgot how we numbered it previously, but I'll just renumber it this way. And this is 1, 2, 3. Based upon what is drawn, is 3 going down or up? Down, right? Because we're sort of looking at it this way. So that's going away from us. And then this one is coming towards you. Right? So correct. So this would be the answer. And then the question, so I think it's probably best to sort of draw it this way first. And if I ask you to relax it and open it up, when I rotate around that bond to make this go from syn, right? So now we're sort of, what's in this form right here, this is reflective of sort of, I guess you would say it's sort of an eclipsing, fully eclipsing, right? That these are sort of, these are syn to one another, right? If we drew a Newman projection down this way, they would be on top of one another. So we're going to rotate it a full 180 to make them anti, and what's going to be the relationship? You have your hand up? Okay. But when we do rotate that around, so what did your hand tell you? Exactly. So once we rotate it around, all right, well, we'll start with, since this one's kind of 1, 2, 3, 4, 5, 6. We're sort of closer, I guess. Yeah, because then we just rotate around. So 4 is a little bit closer to being seen here. So if this is 1, sorry, if this is 6, 5, 4, you sort of notice that that stereochemistry is this way. And you're 100% right when you, because now we have to tilt this way, rotate that around, and then this would be coming towards you as well. Okay? So again, this is how you go about figuring out the stereochemistry of a co-rearrangement, of a Claisen rearrangement, of any of these sigmatropic rearrangements. Okay? So let's try another one. And I'm going to sort of complicate it a little bit, where I will introduce additional stereochemical features. Oh my god, it's 10:30, time flies, yeah. Okay, so I did multiple rotations in my head. So the first one was I took this and I rotated it 90 degrees this way. And so when I went to 90 degrees that way, so if I took this molecule and I basically moved it that way, and I got this. You see that? So I just basically moved this way a certain percentage till I got this, so that the stereochemistry here sort of reflected this here. Okay? That, then I just simply rotated around that bond in my head, right? Which is irrelevant to the stereochemistry, but it gets it to this orientation. That's not going to change anything, simply rotating around that bond. Right, that just gets us looking something more similar to that. Then you want to sort of rotate around that bond there. Okay? When you rotate around that bond there, again, it's axial here, so you're going 180. So you're basically taking this methylene, you're going a full 180 to the point at which this, instead of being eclipsing, it's now going to be anti. The stereochemistry here hasn't changed. We have a proton coming towards us, right? So when we go around 180 degrees, now this methyl group here is going from that way. Now you flip it 180 degrees, now it's going to be coming towards you. And then I just rotated that one as well to get it to look like that. So, okay. All right. So 10 minutes. All right. So we'll start to throw one up here, and I don't know that we're going to necessarily be able to get through this given the time that we have, but I'll throw one up. It's going to be a little bit more of a challenge, but it's one that's at least worth starting to discuss. And in general, I sort of showed it going in this direction, and you may get questions that'll go in one direction or the other. If I sort of ask for going in a specific direction, recognize that this is a reversible process, and so generally what's going to happen is whatever the product is that's lower in energy will be the one that's going to form, but really what I'm focused on here is stereochemistry. So if the product technically is higher in energy at this point, I'm not going to worry about that at that point, this time. I just want to sort of have some problems so that you guys can think about stereochemistry. Now, if the molecule,
That's not symmetrical.
that's what I'm going to do. Okay, so I'm going to put a stereocenter on this molecule. And so I've basically taken the exact same molecule that we had before, and I'm going to put an isopropyl appendage on there. And the question becomes, what is the product? And here's the thing. So I think it was Saul, did you ask that? Did you ask what happens if it's not symmetric?
Oh, yeah.
Yeah, so the question is, what happens if it's not symmetric? This case, it may be the case, and this might make this one a little bit more challenging, it might be the case that the first chair that you draw might not necessarily be the one that's the lowest in energy, right? I've thrown an isopropyl group there, and now, while the alkenes are always going to be pseudoaxial or equatorial, Tosh? Are the alkenes going to be in the transition state? Because they're both trans, just like before, are they going to be pseudo-equatorial or pseudo-axial, do you think, if you remember from the last time? What's lower in energy, trans or cis? Trans. What's lower in energy, equatorial or axial? So for the same reasons, the trans will then be equatorial, right? Because it's about the proximity and the relationship between everything else. So those are always going to be pseudo-equatorial. The difference that we have here that's going to make this one a bit more of a challenge, and I'm not sure that I'm going to give, I don't know, we'll see. I don't want to say anything about the quiz level of difficulty, but certainly on the exam you will see something of this level of difficulty. Whether or not you see it on the quiz or not is up to how I feel when I'm writing them. But you have to recognize that there's going to be two types of, there's really going to be two enantiomers. So not only do we have an issue of diastereoselectivity, selectivity, there's going to be an issue of, ultimately I think, of enantioselectivity. So the first question that I'd like to get an answer up there on is just, without worrying about stereochemistry, and there's two types of stereochemistry now, right? There's both sort of these two sp3 stereogenic centers, but we're also going to have alkene stereochemistry, right? Got about 7 minutes. So, all right, so let's go through what the product's going to be. So instead of calling somebody up here, I'll just sort of ask you guys as a group. So again, we want to draw our electrons going around the system. Where's my other chalk? Right, which means right, we have a single bond that becomes a double bond. Again, just sort of around. This carbon here is this carbon here, right? There's going to be a methyl group here. There's going to be a methyl group here. And where is the isopropyl? Second? It's on the same carbon, right? But which carbon is that? That bottom one?
No.
That bottom. Good. Okay, so, and here, I'll put a squiggly line for the isopropyl group as well, because not only do we have questions about the stereochemistry here and here, but there's going to be alkene stereochemistry that's going to be introduced as well that we have to look at.
It's not a stereocenter.
It's not a stereogenic center, but it's a component of stereochemistry. Okay, Jessica's looking like either she's fallen asleep or she's nailed it. Or something else. Yeah.
So if the double bond start off as the E, you guys know?
So if the double bond starts off as
Yeah, as the E, then the product has to be E also.
So yeah, I mean, let's take a look at this, right? So here's the chair that we have, okay? We'll have to base ourselves somewhere. Now we have a stereo center here. We know that these are going to be set regardless, right? Those are both going to be trans, right? Okay? And what we have to worry about now is that isopropyl group. Okay? Yeah,
Is it
Carol.
gonna be cis? The isopropyl?
Let's discuss it. It could be, depending upon the transition states that you go through, but this is where we have to consider a couple different forms of it. Right? So, as is drawn here, if I set myself 1, 2, 3, 4, 5, 6, and I went 1, 2, 3, as is drawn, would the isopropyl group be going, would it be axial or equatorial? It would be equatorial, right? Do you guys like that as a sort of a pre-transition state assembly? I do. Because everything is, I mean, your alkenes are going to have to be just based upon their, you don't really have much control over it. But you've basically put this isopropyl group in the equatorial position. Now, if we were to do and it's not a full-blown chair flip, but you can, and I'm not sure that we're going to have time, I'm nervous, I'd like to just sort of finish this up, but you can certainly redraw this in a way where that would be axial. Now, what we're going to see, right, and this can be looked at one of two ways, so I'm just going to make a comment, and then we're going to show it. But there is a concept that you guys might have heard about that is called concept of this microscopic reversibility, right? Like, what happens in one direction is basically the transition state of the reverse direction. So that the sort of, however you're going to go in one direction, the other direction is going to be the same. And this becomes much into play with stereochemistry, right? So if in the transition state, as we've seen, a trans double bond in the product ultimately becomes equatorial. If we were to go in the reverse, that pseudo-equatorial would become what? A trans. So this is a sort of concept of microscopic reversibility. So this alkene that we've shown here, right, it is equatorial. So when we ultimately do the sigmatropic rearrangement, it's going to also become trans. Now, Turel, I'm betting that you initially had it in the axial configuration, perhaps. Because if you did do it through the axial, then it would lead to the cis. So you just have to redraw it, figure out a way to move it around to get it to that other way. And the reason why you can sort of see this, right, is that these protons, what's the relationship between these two protons? They're kind of anti to one another. So in the product, they're going to be anti to one another, which means the relationship between this carbon and this carbon, right? So this is going to become equatorial. A lot of times I just like to draw that dotted arrow to sort of complete my chair. But yeah, this is now anti, right? And now the perhaps challenge can become the absolute stereochemistry that we get at those carbons here and that we get here. And so we got about like 1 minute. But if we're going to consider this molecule as is drawn, I think it's worth it to just sort of think about, that's trans. This would be the first methyl group here. Is that coming towards you guys or away from you guys? Towards us. What about this guy over here? It's going to be going away, which is kind of what we discussed before. And that's going to be the ultimate absolute stereochemistry. So unlike the last time, so this comes to what Saul was asking about when something is desymmetrized, this is an instance where the stereochemistry that is here will relay the sort of the absolute nature of it to the stereochemistry over here. So depending upon whether this is R or S, that's going to determine the absolute stereochemistry over here. So again, you guys should be able to rotate and do these other things. So, all right, so good luck on the quiz. This does take a little bit of practice, so make sure you give yourself enough time to really go through some of these. And again, you can make up some of these questions on your own, right? Make dienes and so forth. So, okay?